And recording, can we start, sir?
Yeah, recording just few minutes, huh?
Okay. 6:05 we'll start, sir.
Yeah, I kept ready state, ma'am. 6:05, I'll just make it, ma'am.
Okay.
I think you can start the program. Recording on.
Ma'am, Akila ma'am?
Ma'am, I've initiated recording.
That's okay. Would you like to start your talk?
Yes, ma'am.
Okay. Please go ahead. Yeah. Presentation and...
Good evening to one and all present here. I welcome you all for this webinar on game theory and applications in operations management. I welcome all the members from the various organizations and also the speaker, Mr. Professor R.K. Amit sir. And I would like to welcome Mr. Linesh SanatKumar sir, President, Hindustan Chamber of Commerce, to welcome to provide the welcome address.
Good evening, one and all. I have a great pleasure in welcoming the speaker for today's webinar, Professor R.K. Amit, Department of Management Studies, IIT Madras. I take pride in welcoming Mr. H.R. Mohan, Chairman, and Mr. Hiren B. Shah, Co-Chairman for Information Technology Committee of the Hindustan Chamber of Commerce. I heartily welcome the Executive Committee members of IEEE Chennai, ACM Chennai, Computer Society of India, and in particular, Dr. Komathy and Dr. Sakthivel. For this webinar, jointly organized by all the organizations, we have gathered here to understand the game theory and application in operation management. As far as I understand, game theory is a mathematical subject that is commonly used in practical life. It is applied to various other non-mathematical fields too, Game theory explains how a strategic game is played. It determines the way or the order in which the player should make moves. It considers the information for the player at each decision point. Well, this is only a layman's understanding. We have with us our expert, Professor R.K. Amit, who will enlighten us as to how it is used in operation management. Having said that, I would just say share a few words on the chamber. Hindustan Chamber of Commerce is a 78-year-old chamber with closer to 1,000 members. Most of them are from the MSME sector and covering various trade and industry, right from manufacturing sector. And also we have certain professionals like chartered accountant, auditors, who are also part of it. We have been conducting various programs for the benefit of our members and business community at large. And we also publish a monthly journal. And experts from various organizations are requested to contribute articles to our journal. I once again welcome all of you all. Thank you very much, and handing the proceedings to HR Mohan, sir.
Thank you, sir. Now I request Mr. HR Mohan, sir, Chair Events, IEEE Madras, to introduce the speaker.
Greetings and all. Once again, on behalf of the organizing units, Computer Society of India, IEEE Computer Society, JCM and Hindustan Chamber, I extend warm welcome to our esteemed speaker, Professor Amit, members and my colleagues from the organizing unit, participants who have joined the Google Meet meeting, and those watching the event through the YouTube streaming. Operations research as a discipline has provided a lot of techniques which are used very much in our day-to-day life. This utility of these techniques become much more impactful after the automation using the information communication technologies. While the use of game theory, one of the OR techniques in modeling operations and supply chain management, is well recognized, its underutilized concepts and tools could strongly influence several operations management problems. Further, with the increasing digitization of operations and supply chain management, the narrative problems in these areas focuses on blockchain and smart contracts, platforms, and shared economy. Today's presentation will be on the new issues being predominantly multi-agent settings and lending themselves to game theoretical solution concepts, and focus on different strategic situations like games in normal form, games in extensive form, games in incomplete information, mechanism design, and cooperative games to solve operations problem of supply chain coordination, capacity planning, revenue and pricing management, and other complex problems of matching supply with the demand. With this brief intro of our today's webinar topic, game theory and applications in operation management, let me formally introduce our speaker. Professor Amit was known to me for about 2 years since I came to know about his editing the book Advances in Digital Manufacturing, highlighting the various facets of Industry 4.0. We at IEEE Computer Society had organized an exclusive one-day event with him as a key speaker. And knowing he had authored another book, Game Theory and Applications in Operation Management, I was very keen his vast knowledge should be made available to our members at large. Professor Amit is currently a professor in the Department of Management Studies at IIT Madras. He completed his undergraduate studies at IIT Kanpur and his doctoral studies at Indian Institute of Science, Bangalore. At IIT Madras, Professor Amit heads the Decision Engineering and Pricing, which is popularly known as Deep Lab, which specializes in engineering the best decisions using the wisdom from optimization, game theory, and mechanism design and pricing. Engineering of decision has become a vibrant research area, challenging the traditional tools in modern management. Deep Lab is leading the transition with high-quality publications in top-tier journals. Deep Lab is also working on numerous contemporary industry-relevant research themes in revenue management, healthcare, electric mobility, sustainability, and digital manufacturing and supply chains. With this short note of introduction, let me now request Professor Amit to enlighten our members on game theory and applications. Over to Professor Amit.
Thank you, sir. Now I request our speaker, Professor R.K. Amit, sir, to give his presentation, and you can share your screen, sir. Thank you, sir.
Is it visible? Can you see that?
Yes, sir. But it is on the edit mode.
No, I'm just doing. Is it visible now?
No, sir, it is edit mode, sir. It's not display mode. It's not in the display. Yeah, gone.
No, I'm just doing. Let me see if it works out. Otherwise, I will share the full screen.
Yeah, now. Yes, sir. Now presentation mode. Yeah, presentation mode, sir.
Sure. Okay. Is it visible what I'm writing also?
Yes, sir.
So, I think thank you and thanks for the introduction, and I'll try to keep it within the time because the subject is sufficiently vast. I try to minimize the number of slides, whatever I can do. And I think I've titled it Game Theory, a Curtain Raiser, because I'll try to emphasize more on the application side of game theory. So let me just start with the brief introduction about the book. So this is the book which I think this came about 3-4 months before. And as Mr. Mohan talked about the lab, so our lab is called as Decision Engineering and Pricing Lab. We call it Deep Lab as an abbreviation. And the book is Game Theory with Application in Operations Management. The book came in sometime in June, published by Springer. And the book is written in a form that it actually tells you not just about game theory. It also actually tells you about a lot of the things which goes as part of the game theory in terms of decision theory, in terms of operations management, in terms of optimization, in terms of OR, I think, as Mr. Mohan was mentioning. So the book actually has, you can say that it is an integration of multiple streams and multiple ideas. But the main idea is always game theory, and that is where the title reflects the game theory with applications in operations management. And I'll start with some simple examples, then go into some theory part of game theory, and then we'll conclude with maybe a slightly, you can say, contemporary application of game theory in business. So I'll start with a very illustrative example, and I think this example should sufficiently tell us what game theory is all about. And this example is given by a mathematician called Bress, and that was way back in 1968. And we call currently this as a paradox. We call it Bress paradox. And this will highlight what game theory will actually do. And we'll also look at some of the solution concepts which comes as part of game theory. So as I think in the introduction, Mr. Mohan talked about different representations of games, like games in normal form, extensive form, and the characteristic form. So this will be more of a normal form representation. So the story goes like this, that there is a origin and destination. In this example, the origin is A, the destination is B, and a set of vehicles have to decide which path to take, and there are two paths. One is ACB and other is ADB, and whatever is given as part of, if you see the numbers there, 45 x by 100, that is the travel time in minutes. And what X actually tells is the number of vehicles which are actually on that particular segment. So assume that if 100 vehicles are there on the segment AC, it means that the travel time is about 1 minute. So this X by 100 is again time in minutes, but it is X is the number of vehicles which are actually on that segment. So this example, all these numbers are more or less constructed, but this, as I mentioned, that the goal here is to actually see what game theory is all about. So in this case, we can start with maybe in a particular day in the morning. A could be some origin, maybe we can think of ID itself, and B could be some destination, which could be, say, Mahindra City in Chingalpet. And this could be the travel time, and there are 2 routes through which we can go there. So I'm just assuming some numbers there. So assume that we start with 4,000 drivers who are starting in the morning, and they have to decide which route to take. And their goal is very clear. They want to reach their destination as early as possible. So in fact, when we use something like a Google map, invariably we are actually deciding which route to take based on the recommendation which is given by the map. So in this case, there is no recommendation. They just have to decide, and their goal is to actually reach as early as possible. So in this case, if you look at the numbers AD and CD, the travel time remains constant. So we can assume that they are connected by maybe an expressway, maybe a high, you can say, the number of lanes are large, so the travel time is more or less constant. It is independent of the congestion on the road. So if you start with a very simple example like this, we can always think what would actually happen in the equilibrium. When I say equilibrium, it means that you actually settle on something where no one wants to deviate the path, whatever they are actually taking at that point of time. So if you look at this one, even if all 4,000 start taking ACB, gradually they would realize that there is alternate path where they actually can take less time. But in the equilibrium, we can easily make out that 2,000 will take this one and 2,000 will take this one, and the travel time would actually be 20 plus 45 is 65 minutes. So whether you take ACB or ADB, the travel time will remain same, 65 minutes, independent of which path you take. Because anyone wants to move to the other path, the travel time would actually go up because the congestion would actually go up. In the equilibrium, the travel time is 65 minutes, independent of whether it is ACB or ADB. Now, what actually happens? Assume that some new technology comes in, and which says that we can actually connect AD with a very high-speed link. But only thing in this case, the path is you can only go from C to D. The inverse is not possible. You cannot go from D to C. So in this case, the path is defined from C to D. I can think of a technology like these days we talk so much about a Hyperloop, which says that it would be a very fast travel link between two points. So in this case, the points are C and D. And zero not necessarily has to be zero in the real sense. It could be a very small percentage of the travel time compared to the travel times on the other segment. So when I say zero, you can think in terms of the percentage. For time being, let us assume that this is a very high speed link, which is getting connected between the point C and D. Okay. Now the situation is different from what is in the top figure, and something interesting would actually happen. So if you look at the equilibrium path now, what everyone wants to take is the path which is something like this. And you can easily make out why the equilibrium path should be like this, because we made the assumption that the drivers are looking to minimize their travel time. And we will make that assumption about game theory, as I think it was mentioned in the introduction also, that we are talking about the strategic players. So currently our drivers are deciding on their own. They want to minimize their travel time. And if you actually see this, the travel time on this segment is 40. Travel time on this segment is 40, which is less than 45. So they would actually take, all of them will take this path, because even if all travel, the travel time remains 40. Then they take one, and if they reach at this point, at the point C, again, if you see, this is 45 and 40. And total travel time would actually be now, instead of 65, would actually become 80 minutes. And you can easily verify that, if any driver wants to deviate from this equilibrium, the travel time for that particular driver will actually go up. So if everyone else is following this path, then you try to deviate from this. Like even if you take this one and then you try to take this one. So this will be close to 40 and this will be 45. So this will be 85 and your travel time would actually be higher than 80. So no one actually has an incentive to deviate from the green path, which is marked here. And this is what we actually call in game theory as a Nash equilibrium. So in the previous case, the Nash equilibrium was 65. In the second case, the Nash is 80. But this is a paradox because the original idea was to reduce the travel time when we actually built a high-speed link between C and D. So I think one thing which is should be clear here is this is a constructed example and there are multiple variants of it. And the outcome in this case is inefficient because the travel time actually has gone up in the equilibrium, and we call it the price of anarchy. And we'll discuss it further, I think, as we go along into this. But when I say price of anarchy, in this case, it is the ratio of what was the outcome in the bad equilibrium over the good equilibrium. So 65 was happening earlier and now it is 80. So 80 over 65 is actually the price of anarchy. And this anarchy is coming because everyone wants to look at their own self-interest. They want to minimize their travel time, and this is where they actually end up. So this is just an illustration of what game theory is all about. So I think in this case, if you look at, we started with the assumption of the independent drivers. They so they have a goal, they want to minimize their travel time. They also look at how to actually make the choices. So they are intelligent enough to actually decide which path to take. But in the end, the overall outcome of the setting is the travel time for them. Each one of them is actually higher than what they were actually getting in the previous one. And this has been observed in practice also. In fact, there are examples, there are real examples where when they actually construct a flyover, the travel time actually has gone up because everyone wants to start using the same thing. The congestion is higher and the travel time actually has gone up. So there are examples like this. So let me go further on. We'll come back to this in some other form, but let me go further. So let me give you some background, and let's start looking into what we call as the nuts and bolts of game theory. We'll call it primitives of game theory. And as we go further into it, the emphasis would actually move from talking about just nuts and bolts and to see like where game theory is actually used in business. So let's start with a very simple definition of it. When we say game theory, it's a study of strategic interactions between rational and self-interested agents. We'll talk about what rationality means and what self-interest means. And the theory is mainly normative. When I say normative, it means, as Mr. Mohan was talking, the whole of optimization is normative. It is mainly a prescription. It is mainly some kind of a, you can say, decision support, which tells if the players are, like in game theory, the players are rational and self-interested, what they actually should do rather than what they are doing. Okay. So this is the normative part of game theory. In fact, now the game theory is actually getting deviated towards the behavioral side also. So they want to see the descriptive part of game theory, what players are actually doing. But the main idea of game theory is about giving more of a prescription to the rational players. So if you are rational, this is what you should do. So in this case, in the previous example, if you see, so Nash equilibrium is again more of a prescription for the rational players. There will always be deviation, and in fact, sometimes as in the introduction, I think it was talked about, the information changes can also change your choices. So you sometimes give different information to different agents. So if the previous example, if you see, this is what you would actually see. So let me keep on going. I think, so game theory is not new. I think people associate game theory with the time of John Nash or von Neumann. But it starts with the great mathematicians like Leibniz, Zermelo, Borel, and they actually, that point of time, I think during their time, they were looking into the game theory from the perspective of balance of power, which powers are more, you can say, more central, more important. And some of these ideas still reflect because there is a lot of emphasis on political game theory. In fact, there is a full stream of that, which looks at including what is the power of a party or a power of a MP in the parliament. So these are some of the things which were at the beginning of game theory. Leibniz, in fact, gave the initial version of what we call as a Maximin theorem, which becomes more like the fundamental theorem of game theory. So let me keep on going. So these two, as I mentioned, that von Neumann and Morgenstern, the ideas of game theory were there for a sufficiently long time. And von Neumann we normally associated with the modern computer science also, but he is one of the original thinkers in game theory. And the book came in 1944. The fundamental result of Min-Max theorem he proved in 1928. And if someone still has to start reading game theory, I would still say that this is one of the best starting points to understand game theory, because they actually could foresee a lot of things which actually, you can say, the game theorists worked on for the next 50 to 60 years. It's still some things which they actually mentioned in the book are still not resolved. I think people still keep on working on them. So this is still a good starting point. I think there was a comment yesterday, which is the starting point for game theory. I could, instead of reading any other book, I would still prefer someone to read the theory of games and economic behavior. So let's come to the more central nuts and bolts. So when we talk about game theory, we talk about, as mentioned earlier, it is about the study of strategic interactions between rational and self-interested agents. And in this case, the agents are the decision makers. And as Mr. Mohan mentioned, we call game theory also as multi-agent systems. So game theory, I think, for some historical reason, the name is struck, the nomenclature is game theory. But we can always rephrase it and call it multi-agent systems. And it is something which is part of the computer science. It is part of economics. It is part of maths. It is part of management. It is part of psychology. It is part of philosophy. It is part of biology. There are a lot of people who work actually on, in fact, one of the very famous book is by Richard Dawkins called Selfish Gene, which talks about the evolutionary theory of biology using game theory. So survival of the fittest can actually come as part of game theory. So we have multi-agent systems where we assume that each agent is rational, self-interested, and strategic. And when I say the agents are rational, it means that they are intelligent enough to compute what is best for them. So they are wise. They know what is they have computational capability to compute what is the best path, like in the Brest paradox, or what is the best choice to make. So they take the decision based on that. And they are self-interested. It means that they are looking what is best for them. So in the first case, when I say rational, it means that they are intelligent. Self-interest means they are actually intelligent for themselves. They can know what is best for them. They know what is their payoff, what is their utility function. And they are also strategic. It means they want to drive the outcome of the game in which path, in which they actually get a better payoff. So this is more of a trait we assume for the agents. And with this assumption, with these behavioral traits, we assume that they will actually take a path or make a choice which gives them the maximum benefit. So this is something which is, you can say, very fundamental as part of game theory. In fact, we make multiple other assumptions. So one of the assumptions is what they know about the game. So we assume that can you see it went up? Sorry. Yeah, so one of the assumptions we make is that they just don't say that we are rational, they believe that the other players are rational, and they know that the other player know that they are rational. So this is something which we call as rationality is common knowledge. And then like any game, we always have the rules of the game. So in this case also the rules are there. So when I say rules, sometimes the rules are given from external agencies, but sometimes the rules are actually devised by themselves. And when I say rules, it also means that who will actually make the first move, who knows who will make the second move, all those things are part of the rules. And there's something which is very important is the information, what they know about the game. So sometimes we have games of complete information. It means that the players know who is the other player, what is their payoff. All those things are part of, like in the, if you look at our breast paradox example, in this case, all these numbers were known to the drivers. So based on that, they are deciding. And they are assuming that the other drivers are equally rational. So all these things are assumed as part of game theory. So information is something which is very critical, and as part of rationality, it is important to understand that when the information changes, the actions can also change. So sometimes that is where these days a lot of people are modeling game theory to look at the dispersion of the fake news. Okay? Because when we have fake news, the information changes and you actually can manipulate the actions of the agents. And even if they are taking the best action for themselves, but that is based on the information which is not correct for them. So this is something which comes as part of it. And then we have two more classes of games. So these are the broad classification, and this is coming right from the time of von Neumann. We have non-cooperative games and cooperative games. When I say non-cooperative games, we are talking about the games where the modeling unit is a single player. Communication is actually modeled. When we talk about cooperative games, modeling unit becomes a group of players and communication is assumed to be exogenous. Because communication is actually part of the rules of the game. What can be communicated, what cannot be communicated. So when I say communication is modeled, it means that we decide the protocol of communication. I'll take for an example, I think that will make it more clearer. And then we also have the modeling unit is in the cooperative games, the communication is assumed to be exogenous. The modeling unit is a group of players. So if you look at the business examples of it, if I have to model an alliance, say between two automotive manufacturers, say Mahindra and Ford, I would actually prefer to use cooperative games because in this case, the modeling unit is a group of players. So you look at possibilities, what a group of players actually can achieve. Okay. Then what some of the research points there could be how you actually make that group of players or alliances stable. So a lot of people who work on cooperative games look at the stability as one of the goals. So this is just to conclude this part. This gives an illustration of different types of games. I've taken it as a screenshot from the cover page of book by Martin Osborne and Ariel Rubinstein, 1994. The book title is A Course in Game Theory. And there are four, if you see four boxes, these are the four predominantly classes of games. This we call as zero sum, 2% zero sum. So you can actually see one person is smiling and one is sad. This is an example of a classical non-zero sum game. So zero sum games, example could be any military conflict. So one party wins, one country wins, and the other loses. In fact, most of the research in the initial phase of game theory was actually on zero sum game. And Mr. Mohan talked about war. So zero sum games are modeled mainly as the linear optimization, linear programming problem. And you can always solve them using the simplex algorithm. So then we have non-zero sum games, which are the classical games. Then we have, this is the cooperative games. You can actually see that two people are coming together, and this is more of games with communication. And a lot of business applications are there for the games with communication. And we'll look at some of them. So let me keep on going. Let me just give you one more example before we venture more into the business applications of it. So this is a game in normal form, and we say normal form because this is mainly to model what we call as the simultaneous choices of the players. So we call sometimes these games as simultaneous games. And what that means is player 1 and player 2 are actually making the choices at the same time. So it's not about the time index, the time stamp still can differ. But what it actually means that the choice of player 1 is not known to the player 2. So this is just an illustration which is very similar to the Brest paradox of the equilibrium. So there are two players, player 1 and player 2. Player 1 has two choices, top and bottom, which are represented as T and D. Player 2 has two choices, L and R. And there are numbers which are given. We call sometimes these games also as bi-matrix game, because in each box you can see two numbers. It's like a matrix, but each box has two numbers. So first number is the payoff of player 1 and the second number is the payoff of player 2. And each player wants to make a choice to increase, to maximize their payoff. Means each player wants to do it. So if player 1 wants to look at the outcomes, 11,0 is the best outcome for player 1. And you can actually see it written here. And same thing for player 2. But something which is very evident from this particular example is the best outcome for player 1 is completely diagonally opposite to the best outcome of player 2. You can actually see this 11,0, and so there is some conflict. And we also make this assumption that the players are not talking to each other. So the communication is modeled, and the communication is modeled in the form that there is no communication. They're not talking to each other. They could decide independent of the communication. And if you see these numbers, there is something more to it. If you see these numbers, player 2 actually has a choice which is R, and player 1 has a choice which is B. And the equilibrium in this case would actually be 3,3. I'll not go into the details of it because I want to spend more time on it. And 3,3 in this case is the Nash equilibrium. And it can be easily verified when I say Nash equilibrium, because when I say it's an equilibrium, it means that no player actually has an incentive to move unilaterally and gain. So if player 2 keeps on choosing R, and player 1 chooses B, move from B to T, the payoff of player 1 actually becomes 3-0, and same thing is for the other player. So no one actually has an incentive to move, and you will actually settle on 3,3 when there is a better outcome which is 10,10. And that's where the self-interest part comes in, that self-interest will lead to suboptimal outcomes. And if you see this, 3,3 is actually the third best outcome for both of them, not even the second best. So both of them actually is the third best outcome. They converge on the third best outcome, which is 3,3. So this is just an illustration, and even if you add a component of communication before they play the game, you would still converge on 3,3. And this communication is actually, in game theory, we call as a cheap talk. And this is in fact one of the bases of what we call these days as blockchain. I'll come to that part. So cheap talk is something which talks about non-credible communication between the agents. And that is actually the basis of what we currently know as a technology of blockchain. Well, come on that part, but let me just skip some of these slides because I think we are running short of time. And let us spend some time on this is a formal definition of Nash equilibrium, which is one of the solution concepts for those normal form games. And the definition is very clear that unilateral deviation from the Nash equilibrium should be suboptimal for each player. And that's where when we say, this is the definition which is given here. And when we say Nash equilibrium, it means that it should be self-enforcing. No external agency is needed to implement that. And then we also classify Nash equilibrium as strict and weak. Let me not go into that thing. Let me just stop there for the Nash equilibrium part, which is the definition of that. If the other players are playing their part of Nash equilibrium, then unilateral deviation leads to a lower payoff for each pair. And this is something which is reflective in this example, what we have discussed earlier. So let us keep on going. I think let us start. Let me skip some of these numbers. And there is a fundamental result which was proved by John Nash way back in 1950, that for every finite game, there exists at least one Nash equilibrium, if not in pure, in mixed strategy. Again, that's more of a math result, may not be of much relevance for this particular session and discussion. So let me keep on going into the application side of game theory. Okay. So this is where the business application comes in. And one of the very important applications where you can actually say game theory and computer science intersect is actually the auction theory. And I've just put some slides. We'll try to, if time permits, I'll try to discuss some of these auctions in detail. So you may be aware of the spectrum auctions. When the spectrum is auctioned, if you are aware of the 5G spectrum got auctioned. And auction is something which is, you can say, the high point of game theory in terms of the application. Because all these auctions are designed using the language of game theory. And these are, in our classification, these are games with communication. And assume that this could be the government. They get the bids from the bidders. In this case, it could be the telecom companies like Airtel, Jio, Vodafone, right? And they want to win the spectrum, and they will assume that the government wants to give to someone who is the highest bid. Now they actually will want to bid. They don't want to overbid, which allows them to win. They want to bid with the assumption that other bidders are also doing something similar. And what I have to do is, I don't have to look at the highest bid. What I have to do is, I have to just defeat the second highest bid. So this is the logic which is actually part of what we call as a second price auction. And we call it second price seal bid auction. And even the spectrum auctions are sometimes seal bid. Sometimes they are actually open cry. I'll talk about them. But when I say second price seal bid, it means that the person who actually wins the auction will pay the second highest bid. So I have shown here something called as, this is the old data for Google. They actually earned most of their revenue from the auctioning the advertisement slots. And they actually use a variant of what we call as the second price seal bid. So this is, as of now, let us just, for the placeholder, we can just stop for the auction part here. We'll keep on going. So if you go to something like a procurement portal like Ariba, the SAP Ariba, they also run some of these auctions. In fact, when I'm selling the spectrum, I call these auctions as the forward auctions. And when I'm actually buying something, like in this case, the procurement, we call these auctions as the reverse auction. So if you see any process of tendering, these are the reverse auctions. And again, the auction theory, the language is game theory, because the flavor of games is very, very evident when we look at the auction, as I mentioned earlier. But we look at to a more detailed example. So let me just look at the different applications of it. So this is continuing with the auction part. This is a screenshot which I've taken from the Facebook web page. So it is Facebook business. And this is, if you look at the 2 points, what is written here is this is for the advertisement. And what it actually says is you will often be charged less than your bid, and there is no advantage to underbidding. In fact, doing so may lead to losing auctions you would have been won otherwise. So they are reflecting that they are also using something like the second price, because there is no advantage to underbid. It means that if you underbid, then what you value, you will actually, you may lose the auctions and there is no benefit which comes to that. So this is the logic of what we call as the second price auction. So let me keep on looking at different applications of it. So this is another application in engineering design. In fact, I have taken example for LCA, but in this case, I'm using helicopter, and the light combat helicopter in India is Prachand. And this is about the coordination problem between different teams. So how game theory can actually come for a rescue when we are designing a very complex machine like this. And so this is another example. Let me again skip this one. Let me keep on going. So this is what actually happens, that you really want that the design teams should communicate the best parameters of the design. So what actually can happen is when they look at their local optimization, so the tail gear team may look at the best design for them, which satisfies their condition. And landing gear team may actually look for the best design for them, for their condition, whatever the given conditions, the constraints which are given to them. But they actually end up, both of them has a coordination problem, which is like the Nash, what we have seen earlier, that you may end up at 3,3 compared to 10,10. And it can happen that you may end up with a higher cost and higher weight. So the whole logic of the social outcome, the optimal social outcome is because of that Nash equilibrium, and that is where we want that they should communicate the best parameters for the social outcome, for the best design of the helicopter, rather than just for their own particular component. And this has been observed, as I mentioned, for LCA. So if you look at the LCA story, there is a book on that. You would actually realize the points which I'm just mentioning here, that there is a possibility that the teams are optimizing for their own self goals, and you may end up at a best, you can say worst design than the best design which is possible as a team. I just mentioned about the blockchain in the earlier case about the chief talk, and you can actually see this. When I say chief talk, the communication is not credible. Blockchain as a technology allows you to make the communication credible, as well as it allows you to look at the coordination side. So I have more trust. In fact, blockchain, if you recall, is actually not called as trustful. It is called as a trustless consensus building mechanism. When I say trustless, it means that I don't trust humans, but I trust the technology. And everyone has a right incentives to actually do what is actually in the benefit of the overall blockchain network. So this is the whole logic which comes as part of blockchain. I have multiple, in fact, I have another full deck on blockchains using game theory. But due to paucity of time, I'm just giving one slide which gives an idea that game theory and blockchain are actually interrelated. Because if you read the original paper on blockchain, it starts with the whole logic of cheap talk. So blockchain as a technology is something which is mitigating this cheap talk. It means that it allows the communication which is credible. It does not permit communication which is non-credible. So I think there is a lot of emphasis these days on if you look at the whole logic of automation, machine learning, right? So this is something which again is part of game theory. We call this is an experiment which is happening currently ongoing at MIT, and the experiment is about moral machines. And if you see this, this whole idea is how to actually make the machines ethical and moral. Okay, and if you actually go there, because the experiment is still ongoing, you would realize that how you actually define morality for a machine. Okay, so assume that someone is driving and using an autonomous car, and that car actually has an ethical dilemma, whether to save maybe a pedestrian or to save the passenger. Okay, so how you will actually give the more of a prescription to that machine about how to resolve that ethical dilemma. So this is all about that. So this is maybe at the interface of what we call as a human-machine interface. And again, that is part of game theory, because the agents in this case are still, you can may not say that human to human, but it is between maybe the human and the machine. So this is a very interesting one, and if you see this, it's written there, a trustworthy tech challenge. So some of these things are actually part of it. So this is something which is ongoing. Maybe if you have time, just go there. So a lot of, in fact, I can suggest a very interesting book. Called Human Compatible. This is by Stuart Russell. Stuart Russell is one of the original father of AI. In fact, he wrote the first book way back in 1973. The current the book is in the 4th edition. Russell and Norway, if you might have heard about it. So they, in fact, is there. It's one of the co-authors. So he has written a book called Human Compatible, which talks about how you actually make the machines compatible to humans. And this is a very recent paper. I think it came about 15-20 days back about so the research question here is to look at the obedience of robots. So should robots be obedient? And they actually used in this paper, if you go through it, they actually use game theory. In fact, they all look at the Nash equilibrium. You can see rationality and all those things as part of it. Whether the robots should actually be obedient or they should be disobedient. So this is something which is now ongoing research as part of how we actually make the machines compatible with humans. This could be part of Industry 5.2. This could be part of what we call as HMI, the human-machine interface. But the behavioral dimension of humans, the ethical dimensions or the moral dimensions of robots, somewhere it has to intersect, and you have to look at research like whether the robot should be obedient or we should actually do something which is good for the humans, but by disobeying them. So I think the main result of this paper is precisely this. So this is something which may be part of HMI. Let me keep on going. So this is a project, in fact, which we are doing currently as part of our research, and we are doing with the automobile companies. And the application sites is what we call as the community sensing. And when I say community sensing, it means that we are sensing as a community. Okay. So the example could be, it could be used for multiple things. We are doing for something very specific. So I don't want to go into the details of the project. But if you look at the example, there is a sensing which is happening by individual agents. And these agents could be humans, it could be machines. And they observe something about the ground reality. It could be the market forecast. It could be, say, the risk which is coming in a supply chain. It could be multiple things. And then they report their observations to something like a central planner, which is coming in this. And based on that, you actually get an inference. But then there is a game theory problem here. What you want is the agent should not be manipulative. They should not provide wrong information, because finally their information is getting aggregated at the central planner level. And moreover, so it means that they should have right incentives to tell what actually they observe. They should also put an effort on it. And moreover, they should put an effort to get that information. So they should not just tell something which may be a cheap talk. So this is a part of community sensing. I'll give you an example for that. Something which is happening now. In fact, it is happening with some companies. In fact, Madras has some startup on this, what we call as the community sensing for the environment, for the weather. And this could be for the air pollution. So if you look at the pollution sensors, they are very sparsely located. So now what actually can happen is you can come up with very frugal sensors, which could be at your rooftop. They collect the information, and then you pass that information to a central planner, which in this case could be someone who is doing the aggregation. And there is an incentive for you to provide the right information. So it means that the sensor should be calibrated, and you should see value in making that sensor working. You communicate whatever is the correct thing. Okay. So all those things are actually happening as part of what we call as community sensing. And some people are in fact putting all the data which is coming as part of the sense data or as part of community on a blockchain. So if you see the right side of it, it just mentioned about that. Is it possible to design a mechanism to achieve a consensus about the true state of the information in a network when nobody can be completely sure who can be trusted? So this is something which is happening as part of, you can say, and at the back end of this whole logic is game theory. We designed this like a mechanism design problem, and we want to see that then the agents have an incentive to not manipulate the information. They should provide the right information, and this actually can be used even for controlling the fake news. So some people are actually working on that side also, but for time being, we are doing for a very specific thing for the automobile sector, and we are calling it community sensing. So this is something which is happening. In fact, now the sensors are very, very small. And this is not a crowd sensing. So there is a word called as crowd sensing. When I say crowd sensing, anyone can provide that information. When I say community sensing, it is only very specific agents who are actually part of it. So this is another example which we are doing with the ambulance service called 108. You may be aware of this ambulance services. So they work in what we call as the PPP mode. So they operate in about 22 states in India. And if you look at the ambulance, this is a very critical service because it provides maybe like the first response in the case of an accident or a medical emergency. And they have some, you can say, threshold response time. So if you look at 108, their threshold response time is about 10 minutes. They want that whenever they actually receive a call, within 10 minutes, an ambulance should actually reach the site, the location. So it becomes very important that you want the location becomes very important where the ambulance should actually be located. And we use game theory as part of it. And we use cooperative games, not the non-cooperative games. Because I mentioned earlier that when we talk about the cooperative games, we are looking the modeling unit as a group of players. And I'll explain what that means. And the paper, we recently got a paper, I think last year sometime, we are calling it repositioning game for ambulance services. This paper is with acknowledgement of the data provided by 108. And this is for the city of Chennai. So, if you look at, this is a geo plot of the city of Chennai, and these red dots, if you see, are the locations. So these numbers may change because when we were working with them, around 31 ambulances were operated. Now I think we have many more. But these were the, what we call as the locations where the ambulance are actually placed, located. And they want to do some kind of repositioning. They want that I should know which is the most important location if I have only one ambulance available. They want to maximize the coverage. When I say coverage, they want it should reach within whenever a call comes, it should reach within 10 minutes. So people have done a lot of over on what we call as location science. But in this particular example, we try to combine that over along with the ideas from game theory. And some of you may be aware, when you look at social network analysis, there are centrality measures which tells in a given network which is the most important node. And we are doing something very similar here. We use the logic of what we call as Shapley value. And when I say Shapley value, it actually is a centrality measure which tells me which is the most important player in the game. So each of these locations or each of these ambulances becomes like a player, and we have to identify which location is most important. And we use the idea of Shapley value to actually compute which is the most important. In fact, we did the ranking of all 31 locations, and we come up with what we call as a contingency table, which tells me that if I have only one location, where that ambulance should be located at a given point of time. And that contingency table was also dynamic. Based on the day, based on the time, it keeps on changing. But it actually gives more of a prescription to the operators of 108 that which location is most important at a given point of time and where the ambulance should actually be located. And the results seems to be very, very good because we could substantially improve the coverage with this particular model. And we are in the discussion with them, can we actually deploy this? So this is which is happening in the city of Chennai. So how much time I have? Sir, how much time?
Yeah, can speak another 15 minutes. Another 15 minutes.
Sure. Okay. Yeah, so that's fine. So I have because I've talked more about the different areas where game theory is useful. In fact, I've missed many things also. Deliberately, I've done that because I want to spend some time on what we call as the keyword options, just to give an idea about the kind of business implications it actually has. So this is something which we do every day when we do some Google search. And if you see, if I search something, maybe I'll show you through a slide. So when we search something, some output would come, and some of them are actually come as part of advertisement. So we call them as advertisement slots. And these advertisement slots are actually based on what we are searching. So I'll just give you some background of it. And I think that will give you some idea about what we are doing here. So this is a very important business application because a lot of research still is ongoing. And something like LLM, this actually goes to a different level altogether. So the original internet advertisements were very similar to the newspaper ads we see today, even at that point, which we call as more like the banner advertisements, and which means that when you want to advertise something like shoes or hotel, you just pay and they will not look at whether it is actually going to the right user, whether it is going to the right customer. They say that so many times the advertisement would actually be displayed, and based on that, you make the payment. So it is something like very similar to the newspaper ad what we see today. So this was something which started with Yahoo. So people when we were doing our BTech at ITK, the internet just started. In fact, when I joined IT Kanpur, then only I come to know that there is something called internet. And the initial search engines were like Alta Vista, Lycos, Yahoo came slightly later. But the advertisements were mainly the banner ads. Then suddenly something happened because by the late 1999 or 2000, the Google comes into the picture, and the whole algorithm of page ranking and AdWords, they started with what they call as the keyword-based advertising. So what they did is they look at the intent of the user. They said that if someone is searching for hotel, say in Chennai, this is something which they want to see. So the advertisement suddenly becomes linked to what we call as the keyword. And that's where they start understanding the importance of isolating the ads from the search results and sorting them in the order of relevance. And this becomes very, very important because for past 20-25 years, if you see, Google is actually at the top of the whole search business we call Googling. Now, because there is some kind of a competition coming from the LLM kind of thing. But for 20-25 years, the whole logic of AdWords was actually at the peak of the advertising. And these days, whenever we search something, not just in Google, the advertisement suddenly start reflecting us based on what we are looking for. So this is the origin of it. And I'm just giving you an example of this. So if I put hotels in Chennai, you can actually see the ads are coming there. And the first ad is booking by booking.com. And if you look at this one, booking.com is actually one of their main customers. So their main advertisers there. And this is still true because these numbers are slightly older. But still, if I go and look at it, booking.com is their main advertising. And these are what we call as a inorganic output. What you actually see without the ad is actually the organic output. And there is a lot of, if you are aware, they're facing a lot of litigation in US for the manipulating these slots. No, not the inorganic slots, but the organic slots. So let me just keep on going on this. So this is something which comes as part of what we call as the auction theory or mechanism design. We are calling them as keyword auctions. And this is, some of you may be aware, it is what we know currently as pay-per-click advertising. And this is actually based on that advertisers only pay if a user clicks on their links based on pay-per-click. So it is not just based on if they see something, it is actually based on the click. And the success rate of an advertisement is based on so we have two things here. One is what we call as a pay price per click, and then there is a click-through rate. And then there are multiple ways in which the auction actually can run. But what Google uses is a variant of what we call as generalized second price auction, which we call as GSP. And the logic is very similar to the second price, that the person who actually gets the top slot will pay the bid of the next slot. So this logic is, as I mentioned, is part of second price seal bid auction earlier. And let me just give you a logic of it, why this is very important. So let us take an example. You can actually make out what the whole logic would be. So assume that someone wants to bid auction a house. Okay. And this could be something which could be a palace or whatever. And there are multiple bidders, say bidder 1, bidder 2, and bidder 3, who are interested in buying this house. And assume that this guy values this at 10, this guy values this at 5, and this guy values it at 2. And let me put these numbers. This is 10 crore, 5 crore, 2 crores. And you run a classical open cry auction. When I say open cry, it means that the auctioneer, in this case the seller, says that you keep on increasing the bids, and when the bids are not increasing, the prevailing bid, the person who has that bid will win the auction, and whatever the prevailing price, that is the price of the house. So assume that you start as a reserve price of 1 and you keep on increasing these numbers, right? At the price of 2, at the bid of 2, this bidder 3 will be out of the auction. The bid keeps on increasing. At 5, this will be out. So the person actually wins the auction does not have to actually pay 10. He has to just slightly higher than 5. So it could be 5.05. So invariably what is happening, if they actually bid it truthfully, this guy would have bid 10, this guy would have bid 5, this guy would have bid 2. But the person who actually wins the auction is paying something which is very close to 5. And that is the logic of what we call as the second price auction. And you take my word that all the modern business use a variant of second price rather than the first price. And that's what is reflected in this slide, that what Google is using is what we call as generalized second price auction. So I'll just keep on going. I'll just show you what it actually looks like. And I'm not going into the details of it, but these auctions again were designed using game theory, and there are a lot of papers around them, a lot of research around them. And as it says that the GSP auction, a search engine page contains a fixed number of possible positions for advertisement. And assume a advertiser J, whose valuation, so this is a valuation you believe is actually for the advertisement. How many people will actually click, and if they click, how much value you will generate for that from your advertisement. So they have a valuation VJ and they submit a bid VJ. And it is assumed that if you look at the slot size, if I go with this logic, so alpha 1 to alpha m, assume that there are RAM slots. We make that assumption that the click-through rate, which is alpha, is higher at the top slot. So if you get the top slot, the click-through rate would be much higher. So this is the logic which is used, and so you actually come up with in the descending order. The person who actually has the highest bid will get the top slot, but pay the price of the bid of the second highest slot. So it means that if you get the highest slot, the price you have to pay is what is actually bidded by BI plus 1, and you multiply it by the click-through rate. So this is the logic which is actually used as part of the Google auctions. So let me just keep on going. We spend not time on this. I'll just show you something which may be. So this is something which is happening now. So Google, in fact, does not look at the bid. They look at something called as the quality score. So it means that they look at the advertiser's quality, and based on that, so you multiply the quality score with the bid, and based on that, your quality score is actually, the final score is computed. And the whole logic, whatever we have discussed earlier, will actually work with the final score, not just with the bid value. So this is just an illustration for that. So this is something which I think should conclude our presentation. So thanks for your time. I slightly overshoot that, but this is the end of the presentation. Thank you.
Thank you, sir. Thank you for your wonderful session. You have incited many of the applications where we can have this game theory. So a few questions in the chat box. I'll just read one by one, sir. The first one, may we use game theory in the different consensus algorithm related to distributed systems like blockchain? Will you please opine on the way to implement it in computing?
So there are multiple ways. The thing is, if you look at the distributed systems, we assume that each node in the distributed system is an agent, and the agent is looking for their own benefit. So they don't the agents may not be looking the benefit of the other agents. So whenever we try to model something with selfish agents, invariably the game theory becomes the language. And this is again, as I mentioned in very briefly about the blockchain or any other distributed system, the game theory tries that whatever is actually getting done or communicated in the network should actually be credible. And so you should have the right incentives. In fact, the whole idea of proof of work is precisely to ensure that there is an effort which comes from the agent before they actually put something as part of the block. So, as I mentioned, that it is very, very important, and I think people who work on distributed systems are invariably using some part of game theory. And all these games are mainly the normal form or simultaneous games. Did I answer that?
Yeah, thank you, sir. Sir, you were talking about the primality thing, no? That they have asked like one question from Dept. But does 10 by 10, give more utility?
Yeah. So I think you can take those numbers as utility directly. So 10 means we are not looking into the nature of utility. So 10 is a utility for player 1 and 10 is the utility for player 2. So you can just take that number as utility. Can you see what I'm writing? Okay, I think there is an issue. So the utility of player 1 is U1 and utility of player 2 is U2. So U1 is 10 and U2 is 10. Did I answer that?
So it is not visible.
No, it's okay. I'm not
Okay.
not sharing.
That's what the question says. Actually, the question asked because 10 by 10 is a utility side.
Yeah.
Why yes. Talking about 3,3? That's what.
No, 3,3 is also utility.
Yeah. But which is better?
10,10 is better.
Yeah, that's what.
But they converge on 3,3 because of their own self-interest.
Yeah. Okay,
Yes,
ma'am. Next question.
Next question, sir. Do we need to have any prerequisite knowledge to start learning game theory?
No, I don't think so because I think some degree of maths is okay.
Yeah.
And, I think a lot of logic goes inside that. And what I presented here is maybe more of a very elementary thing. And I'm still learning. And even after I've spent around 15-20 years working on game theory, I think every day when I get up, I still see that there is still to be something to be read and learned. It is ongoing, and I think it opens up so many things for you once you start actually realizing it. So I feel like there is nothing like a prerequisite, but some degree of math maturity is enough. So I think someone who tries to enjoy maths can always learn game theory. But I feel like there are multiple pretty very well-written books which gives you a lot of different perspective of game theory. In fact, I think the research is still sufficiently deep and ongoing. So my answer in this case is please start. If you are looking for game theory, don't worry about there is a prerequisite form. In fact, let me add this. My first exposure to game theory was during my PhD. So it was not before that. Yes.
So, thank you, sir. Some questions from the time of registration.
Mm-hmm.
Can you share some resources to learn game theory in depth?
Yeah, so I think you can actually see, so there is a society called Game Theory Society. If you go there, so this is you can see a very formal body of all the top game theorists coming together and working on this particular thing. It may be very similar to CSI. And if you go to the Game Theory Society, you would actually see a lot of resources available, including the online videos by a lot of top people who are working in game theory. In fact, most of the books are there available either in the soft copy, or at least they recommend which are the best books on game theory for different people, right from the biologist to physicist to economist. So if you are really want to start something, I think that should be the starting point. And once you go deeper, I think you would realize what are the best resources available.
Yes, sir. Next question is on game application for robo. Explain few interesting algorithms.
Yes, so I think that is something which I mentioned briefly about the human-machine interface. I think a lot of people are working on it. And again, I can recommend some books on it. There are actually books on what we call as planning algorithms. So a lot of people who are looking into, say, robot-to-robot interactions, human-robot interactions. So this is something which means I have not discussed the algorithmic part there, but there are people who are actually working on it. So they want to design algorithms which enable this human-machine interface. I just briefly mentioned about one paper on Chennai. Yes.
Yes, sir. Thank you, sir. Some of the questions I've just asked. Now, if there are any more questions, participants, you just have any more questions, you can just ask the speaker. So if no further more questions, now I request our chair, CSC Chennai chapter, Dr. Komathy ma'am, to propose the formal vote of thanks.
Thank you, ma'am. So in the outset, I thank the organizing units to arrange this webinar today to enlighten us with the growing importance of game theory. My heartfelt thanks goes to Professor R.K. Amit for his excellent presentation of game theory and its application in OR. He defined first the game theory as a strategic interaction between rational and self-interested agents, especially in a multi-agent system with the rules and information. He started with the primitives of game theory with its evolution. He illustrated the basic model of the game using few examples. He highlighted some of the applications of game theory, such as in auctions. Example, he cited an example of selling 5G spectrum. In engineering design, where optimal outcome of the design is based on Nash equilibrium. In blockchain, to mitigate the cheap talk. In moral machines, to resolve ethical dilemma between human to human and human to machine interactions. Human machine interface, making machines compatible to human, example of a robot to be rational, to do beneficial actions to human, and disobedient or to be obedient to human. Community sensing, for example, pollution sensor, aggregating the right information and not making any fake information. Ambulance service, cooperative game is used here to locate the nearest ambulance for emergency medical service. Keyword-based advertising used in search engines. Advertisers are paid either by pay-per-click advertising or setting the price through an auction. Search engine uses options to determine the price, and Google especially uses generalized second-level pricing, GSP. So now my heartfelt thanks goes to Professor Amit for clarifying the questions raised by the participants offline and online as well. I sincerely thank our mentor, Mr. H.R. Mohan, sir, Chair Events IEEE Madras, who arranged this webinar for the benefit of the members. I am thankful to the participants who joined us in live Google Meet and YouTube live streaming. I thank the office bearers of the organizing units and even team members of the organizing units for their support in arranging the event. With these warm words, we move to the end of today's event. Thank you all.
Thank you, madam. Thank you.
Thank you, sir.
Thank you.
Thank you.
A final request to all the participants, please provide the feedback. The feedback link has been shared in the chat box.
So, just do you want the slide deck? Please share with you.
Yes, sir. Yeah, you can give the slides, sir. You can send to us on the group, WhatsApp group.
Thank you.
Okay, sir.
Thank you. Thank you, sir.
Yes, sir. Thank you,
Yeah,
sir.
thank you. Thank you,
Sir,
Professor
Mohan,
Amit.
sir, you can
Yeah.
just say a few words, sir.
Yeah, I mean, it has been a wonderful presentation, particularly